Hello, um, this is Prof. Nanius, and what we're going to do is we're going to do a few examples of the Cauchy Euler differential equations. And we'll do some in class on Monday, but I figure for those who wanted to do a head start on the web assigned homework, yeah, we'll be able to watch this video and do it. So let's go ahead and share that screen and get started. Okay. Now, just to remind you what a Cauchy Euler differential equation is. Now we're going to be working in the context of a two variable, two second order. But generally speaking, a second order differential equation is Cauchy Euler if it's linear, and if the first factor has an x squared, second factor is an x, third factor is a y. So in this particular thing right here, in this, we, um, well, this is what we have right here. So we have an x squared times y double prime. And notice the 2, and you subtract the number of primes, you'll get a 0. X to the first, subtract the number of primes, you get a 0. And of course, x to the 0, and there's 0 primes. So that's, and it has to be in this order like so. So these are all examples of Cauchy Euler um, linear differential equations. This one is non-homogeneous, so we'll save this one for last, and we'll show how we do that. So let's look now, and let's just also give a reminder of how we solve these. So basically, what happens is that if you have a Cauchy Euler differential equation that looks like a x squared y double prime plus b x y prime plus c y is 0, what you do is you attempt a solution of a solution y equals x to the m power, where m can be a complex number or a real number. So if you do that, y prime is m x to the m minus 1, and y double prime is m minus 1 x to the m minus 2. I kind of didn't organize my um, work here. So generally speaking, if you dump this into the differential equation, you'll get a x squared m minus 1 x to the m minus 2 plus b m x to the m minus 1 plus c x to the m. And if you notice, you can factor out x squared times x to the m minus 2. This turns out to be a m minus 1 x to the m plus, in this case, b m x to the m, because that's x to the first power and that's x to the m minus 1, plus c x to the m is 0. Then if you factor out an x to the m, and you assume that x is not 0 here, that's an essential thing for the region of validity. So we're going to go ahead and take the region of validity that does not include 0 and includes all the positive x's. Divide out by that, because there's x to the m here, x to the m here. You get this am m minus 1 plus bm plus c is 0. That's the indicial polynomial. And if we evaluate this a little bit, what we have here is we have a am squared, then we have a minus am plus bm. And this, of course, is a polynomial. This, of course, is a polynomial in m. And so its roots are m is going to equal minus b plus or minus the square root of b squared minus 4 times A times C all over 2A. And what we did in class is as follows. So if we have, and this is what we're going to do here. So we'll formalize our work here. So there's only so many things that can happen if you have this. So if we have 2 real roots, m1 and m2, comma, then the solutions are independent solutions are x is x to the m1, y2 is x to the m2. And it's an exercise to take the Wronskian of this. And what you find out is if you do that, well, in fact, let's go ahead and do this. The Wronskian is the determinant. So we now have x to the m1, x to the m2, m1, x to the m1 minus 1, m2, x to the m2 minus 1. Take the determinant, and we get m2, x to the m1 plus m2 minus 1. Subtract m1, x to the m1 plus m2 minus 1, which is this. And this is not 0 for m2 not equal to m1. So technically speaking, if you have 2 distinct roots, we kind of know what the answer is. So we have 2 real roots. These are the 2 solutions. 2. If we have, let's say we have 2 complex conjugate roots. What we have here is we can now, let's go ahead and call the solutions u instead of y. So we'll have u1 is x, and let's write the complex conjugate roots like this. So that's going to be our m here. So x is alpha plus beta I, and u2 is x to the alpha minus beta I. And by the same argument, the Wronskian is non-zero, so the solutions are linearly independent. Therefore, they're a fundamental set of solutions. But this here is kind of, you kind of say, what the heck is x to the bi? Well, this is x to the alpha. And we use this x to the bi. And this other one is x to the alpha, x to the minus bi. And what we do in calculus or differential equations, if we don't understand how to do the exponent, we take e and log. So this is x to the alpha, e to the log of x to the beta I. And this is x to the alpha, e to the log of x to the minus beta I. Now, by using some of the properties of the complex logarithm, now when I wrote ln here, I made a faux pas. This really ought to be written as log because we're using the complex log with a complex argument. But it turns out that you can still write this using our log rules when taking this out like this. So this is beta log of x I. And this is x to the alpha e to the minus beta log of x. Okay, log of x is real. So far so good, right? You might say, well, that's not a lot better. But if we use Euler's formula and write this as u1 as x to the alpha times, and remember we're using e to the ai as cosine a plus I sine b. Well, if we do that, then we're going to get cosine of beta log x plus I sine of beta log x, right? U2 is this, cosine of beta log x minus I sine of beta log x. Now, here's where we do a little linear algebra. What we do is if we add u1 and u2 and divide by 2, what will happen is that the I signs cancel, and we get x to the alpha cosine of beta log x. And if we take u1 minus u2 and divide it by 2I, we'll get this. So these two, this is what's going to be our fundamental set of solutions. This will be our y1 and this will be our y2. Now in class, I haven't justified this, but then the last case is that our initial equation has a repeated root. And I have not justified this. I will do a supplementary video here. But you have x to the m1 will be solution 1. And it'll turn out that y2 equals log of x times x to the m1 will be the second solution. Now, I haven't justified yet. But what you could do as an exercise is you could take this solution here and dump it in. But and show that it works, and then take the Wronskian and show that this is linearly independent. Or, and our existence and uniqueness theorems will say, well, that's what the solution must be. But to actually get that, you have to do a reduction of order, and that takes a little bit of time. So now let's go ahead and solve some equations. And let's take a look at this one. First one. And we'll move this down here. So let's go ahead and solve this. Now, the very first thing you do is you go to the initial equation, right? In the initial equation, we have a 3 here. So with 3m, m minus 1, plus 6m plus, in this case, 1 is 0. So this is 3m squared minus 3m plus 6m plus 1 is 0. And that is 3m squared plus 3m plus 1 is 0. And does this factor? Well, you can try to you can use a quadratic formula, or you could say this factors as, let's see here. This is the one right here. Yeah, so let's go ahead and try to use a quadratic formula to factor this. We'll save ourselves some time. So m is equal to minus b plus or minus the square root of b squared. That's 9 minus 4 times a, that's a 3, times a 1. Ooh, that's going to be 2a. That's going to be 2 times 3. So I get a minus 3 over 6 plus or minus 1/6. That's going to be 9 minus 12. 9 minus 12 is minus 3. And so what we get is minus 1/2 plus or minus 1/6 square root of 3i. Okay? So that's the roots of our initial equation. So make sure. So here's the solution. So your y1 is x to the minus 1/2 cosine. This is going to be your beta right here. Square root of 3 over 6 x. And I think I screwed this up right here. Log, right? Go back here. Darn it. It's what happens. It still break for me. All right. So it's a square root of 3 over 6 log x. I almost turned this into one of our other things here. So remember, it's a log beta log x. And y2 is x to the minus 1/2 sine square root of 3 over 6 natural log of x. All right, so we got that one. A little rough, but we did it. Okay, so that solves this one. Now let's do this one here. And let's just check the initial equation. The initial equation in this case is going to be m minus 1 plus 3m minus 4 is 0. That's m squared minus m plus 3m minus 4 is 0. That's m squared plus 2m minus 4 is 0. Let's see here. All right, yeah, so that's correct. Now, how does this factor here? Well, let's see. The way I like to do this is let's go ahead and complete the square. We could use a quadratic formula. I'll complete the square instead. So I'll take 2 divided by 2 is 1. So it's 2m plus 1. And then we have a minus 5 is 0. So this is m plus 1 squared. See, I added a 1 here. So if I added a 1, I better subtract 5. So m plus 1 squared is positive 5. So m plus 1 is equal to plus or minus root 5. So m is negative 1 plus or minus root 5. And so our solutions is y1 is x to the minus 1 plus root 5. Y2, and this is going to be valid from 0 to infinity. Both of these. And the next one is x to the minus 1 minus root 5. Okay, so that's that one. Nice completing the square there. See, a lot of this is just algebra, isn't it? Now let's do the next one. So we got this one here. So this one here, the initial equation is m minus 1 times 1 plus 5m plus 4 is 0. That's m squared minus m plus 5m plus 4 is 0. Or this is m squared plus 4m plus 4 is 0. And you'll notice this is a perfect square. So m equals minus 2 is a double root. So y1 is x to the minus 2. Y2 is x to the minus 2 log x. And again, the region of validity is 0 to infinity. Obviously, neither of these functions are defined at 0. Okay. So you can see this goes kind of quickly. And so we had almost everything that you can have right here, right? We had the complex conjugate, we had the double root, we had the 2 real roots. Now, armed with that, we're going to do the very last one. Let's take a look here at this one and notice what this is. Now this one's going to be a little lengthier because what we have in this case is we have a non-homogeneous. Now, since we have a non-homogeneous equation, the very first step one is to solve. So that's step one is solve. We have to solve the related homogeneous equation to get homogeneous solutions. And here, this is Cauchy Euler. So we go to the initial equation. What we get is m minus 1 plus m minus 1 is 0, or m squared minus m plus m minus 1 is 0. Or we get m squared minus 1 is 0, so m is plus or minus 1. So our homogeneous, or our complementary solution, can be written as constant, let's say a e to the, I'm not a, 8 times, I better get rid of this, a times x. I kind of just stumbled all over myself here. So it's going to be ax plus b, 1 over x, because that's x to the minus 1. Or we can say y1 is x, y2 is 1 over x. Now we got to solve this. Now to solve this, the method we learned in class, variation of parameters, will probably be the best method to solve this. But in order to use variation of parameters, we should probably, and by the way, 0 can't be in our interval here, divide by x squared. So let's go y double prime plus 1 over x minus 1 over x squared, y prime. And it's 1 over x squared. This is going to be a driving function. So when we use a variation of parameters, this is going to be your f right here. And for variation of parameters, we know our particular solution will be of the form u1, y1 plus u2, y2, where u1 is minus the integral of y2 f over the Wronskian, and u2 is a positive integral of y2 right here. This is a 2, y1 f over the Wronskian. So we have to do the Wronskian of our two linearly independent solutions to the complementary solution. So the Wronskian is a determinant, and we have x, 1 over x. The derivative of x is 1. That's minus 1 over x squared. We do that, take the determinant, that's minus 1 over x, minus 1 over x. Whoops, that doesn't look like that. So it's minus 1 over x, minus 1 over x is minus 2 over x. I'm going to just check my notes just to make sure that I didn't do anything stupid. I wouldn't put it past myself to do that. And yeah, it still looks good. So it's minus 2 over x. It's still the Wronskian. So u1 is minus integral, while y2 is 1 over x. Remember now, our f is 1 over x squared, 1 over 1 plus x. And our Wronskian in the denominator is going to be a positive x over 2. I mean, well, it's going to be negative here, and then the negative times the negative will be positive. And if we take a look at what happens right here with this particular thing, is we end up getting the integral. The x's cancel, and we're going to get the 1/2 from here. These two x's cancel. We have a 1 over x squared, 1 plus x. Now we got to do a little bit of calculus. And so the way we break this up, we know that 1 over x squared, 1 plus x, is a over x plus b over x squared plus c over 1 plus x. Getting a common denominator, we get a, we've got an x here, 1 plus x, plus b, 1 plus x, plus c, x squared, all over this. And that has to be 1. The numerator has to be 1. So we know that 1 is equal to a x, 1 plus x, plus b, 1 plus x, plus c, x squared. Now try x equal -1. That's a 0. That's a 0. That's a 1. So c is 1. Yay. Not that. Try x equals 0. If we try x equals 0, 1 is equal to b times 1. So b is 1. Okay. So we have b is 1. And then we can try anything you like for the third one. Or we could just figure this out here. So let's go ahead and try x is positive 1. Then 1 is equal to 2. That's a 1 times 2. That's 2a plus, see, that's x equal 1. So 1 times 2 is 2. 2b, we already know that's a 1. And we know the c is a 1. So 1 times 1. So 2a is equal to 1 minus 3 is -2. So a is -1. So finally, we get the integral. Your u1 is going to be the integral of -1 over x plus 1 over x squared plus 1 over x plus 1, which works out to be negative log x, log absolute x. X to the minus 2, add that, so it's -1 over x. And then because, yeah, take that derivative, yep, -1, yep, that works. And then that's going to be plus log of absolute x plus 1. We don't need the c here. So that's our u1 right here. We can expand this a little bit. All right. That's your u1. So your u2 is, let's go here. Your u2 is integral y1. Now that's going to be an x. Remember, our f is this weird thing here. 1 over x squared. 1 plus x. And then remember your Wronskian, 1 over the Wronskian. Well, your Wronskian, however, was -2 over x, so it's going to be x over 2 minus. And then what do we have? It's going to be minus integral 1/2. And look at what happens to the x squared. That's canceled. So it's 1 over 1 plus x. That's easy. So let's just take a look at our final answer then. So your yp is, what's u1? Now we can combine these two here. So it's going to be, looking up here, y1, remember, is the x. And your u1 is this mess here. So it's going to be -1 over x multiplied, plus log of x plus 1 over x, all multiplied by x plus 1 over x, that's your y2, minus 1/2 log of x plus 1. So yp is, if we multiply this, it's going to be minus 1 plus x log of x plus 1 over x minus 1 over 2x log of x plus 1. And then what we do is, to finish this up, let's just get rid of yp and let's just call this the general solution, plus c1x plus c2 1 over x. And that's basically how one of these things can be done in full. So thanks for watching.